this topic itself has nothing to do with wireless. This is just pure math. And we thought this was very interesting. We found that neural networks could be used as mathematical solvers. But of course, my expertise, say domain expertise, is in the wireless communications. So we tackled some difficult problems in wireless communications. But I believe and I hope this framework can be used for different applications and different mathematical problems. Okay. So the motivation is this. Okay, you have, say, very difficult mathematical problems and you don't know how to approach this problem. Okay. So here, what I say difficult, say, if your problem is a non-linear and non-convex, then it's very difficult. So then our approach is this. Okay, first, we know this. When we have this neural network, we supply some input data and we get some output. So, for example, in supervised learning, we use this output for classification or for regression. So everybody, including myself, uses the neural network this way. And this neural network itself is a black box. So we don't care what's going on inside, okay? So SGD is working, backpropagation is working. But in the end of the day, I don't use the weight matrix. I don't care, okay? So I just use the output. But in this topic, my view is this. Okay. I just open up this black box and I take out this weight matrix here, and this weight matrix itself is my solution. So this is a difference. Okay. So we solved, say, several problems based on, say, using this technique. But let me just show you only one example. Okay. So far I have tried to minimize the mathematics, but for this subsection, I need to do some math because, in this case, a neural network is used as a mathematical solver. Okay? We have a transmitter and the receiver, and we have some wireless channel, H. And my objective is to estimate this H, so H hat. And I want to minimize this estimation error as small as possible. That is my cost function. Okay? To that end, I want to design two things. Number one, so-called pilot signal matrix. This is a matrix. So pilot means we just send some known signal sequence, and using that sequence, we can do this wireless channel estimation. But this is a matrix, and the size of a matrix could be pretty large, like hundreds by thousands, could be very large. So I want to design this matrix itself. And the next one is I want to design this channel estimator, the function. So I want to design these in order to minimize channel estimation error. So this is my problem. But this is non-convex and non-linear, and computational complexity is extremely high because you need to design this matrix and each element is real valued. So exhaustive searching doesn't work, obviously not. Okay? A little bit more math. So here I have this channel, and this is a pilot, say, vector. If you collect the vectors, I have a matrix. And so we have some energy coefficient and square and blah, blah, blah. And we have this received signal Y at the transmitter. Okay? So this is my received signal vector, but the structure is here. I have some coefficient, and this X is what I want to design, all those vectors, and H is what I want to estimate, and I have some square and some noise. So this is, I will call this equation 1, which is a little bit complex. Okay. Then now, so this is my problem. So this is the same problem subject to power constraint. Okay. And I want to design again matrix and channel estimator. So my approach in this work is I will use two different neural networks. First one is encoder, next one is decoder. This encoder is used to estimate or design this matrix itself. Second one, decoder, is used as a function approximator. All we know that neural network is a universal function approximator. So this is a simple function approximator, second one. So second one is not very interesting. So everybody does that. But the first one is rather interesting. So here I want to design this matrix itself using the neural network. So the approach is this. Now let's consider pretty simple two-layer neural network with no hidden layer. Then at the input side, I supply the, say, channels. So that is my input channel vector. And now this matrix, this weight matrix is denoted by capital X vector. So weight matrix. And then we have this output. But at the output, as the activation function, we use this, zeta square. Of course, we almost always use ReLU or SeLU or say sigmoid or hyperbolic, say tangent function, but we don't do that. Intentionally, we use this activation function, and then we add some noise using the known distribution of the noise. Then now, the input-output relationship of this neural network is given by this equation too. Y is my output, and H is input, and this X is the weight matrix. But if we compare this equation 2 and equation 1, they are the same. So we intentionally designed our neural network that way. That means equation 1 denotes this channel estimation feedback mechanism. Equation 2 represents the input-output relationship of your neural network. They are the same. So our approach is here, we train this neural network such that the channel estimation error is minimized. Then once this training is done, we don't use this output, we don't use. Instead, we open up this black box and we take this weight matrix. So let us say we just read the weight matrix X, and that is the solution. That is what I want you to design this. So that is what I meant here. Once training is done, open up the box and take out the weight matrix, and that is the matrix we want you to design.